Good afternoon to you. Good morning to you, Adam, and other participants in those places in the world. And good afternoon, good late afternoon, and good evening in the antipodal places, because we have connected participants from those places too. Welcome to Paris and to the International School of Astrophysics Daniel Chalonge-deVega for this last session of the year, 20 sessions already, and for to close a great program of the year, we needed a great lecturer and a great lecture. It's a great pleasure and a great honor to welcome here today again in Paris, virtually, but as you know, Adam, you have an open invitation, continuous invitation. Professor Dr. Adam RIESS, Bloomberg Distinguished Professor, Johns Hopkins University, Space Telescope Science Institute, Nobel Prize of Physics, Daniel Chalonge and Ecole-de-Vega Medal of last year. I will be very briefly, because all the time is to Adam, and then after to discussions and questions and comments. I just would like to remind that we just started our Zoom sessions with Adam here one year ago, last December, where he received not only virtually, but materially, the 2 medals of the school. And this year, in continuation, and in what is a tradition of the school, to a surprise award for his continuous, without stopping, in French we said sans relâche, work on the Hubble station rate, and completely in the scientific lines and way of this school. We thank Adam for that, and we thank too for this title, Surprise, from the expansion history of the universe. This school in his 30 years had plenty of nice and good surprises, and we hope to continue to share these surprises with Adam with us, and also awards. So, Adam, the floor is yours, and please, now we are here to hear you. Thank you very much.
Okay, well, thank you very much for inviting me back. You know that it's been a long pandemic when you return to somewhere you spoke before, and the last time it was during the pandemic as well. So, you know, at some point this has to end so that I can come to France, because I would very much like to do that. When Norma asked me to give this talk many months ago, like many of us, you look at a date, you pick a date, and you think, oh, I'll have my results that I want to talk about, new results by then. And, you know, we're always optimistic. But I got close. I missed it by about 24 hours or so. But I did want to tell you that we're giving a webinar tomorrow, the SHOES and Pantheon Supernova projects team sort of jointly. And so I'll talk about the progress on this whole project, but if you sort of want the latest update, and I'll give you a little preview of it later, but if you want the latest update, you could tune in to this webinar tomorrow that's listed there at the bottom. Okay, yes, I received from Norma and the school just a little while ago something they call the Surprise H-Naught Award for 2021. I think this is, maybe it's the first of these, I don't know, but it comes with a lovely bottle of champagne that you see. I'm jealous of you all. It's 4 o'clock there, so you could be drinking this already. Since it's so early here, I just can't quite bring myself to do that till later in the day, but perhaps I can do that. Okay, so let's get.
You have two.
I have two. Yes, I'm sorry. I drank one already. I admit it. I drank one already. But then the next one
in a different taste. I mean, it's another kind of true French champagne. Is another.
Yes. Thank you. So I just want to remind people why it's so important to measure the expansion rate of the universe. And of course, that's because it's one of the only ways we can learn about the universe. Of course, the universe will be expanding at different points, at different times in its history, at different rates. And so, obviously, there's no one universal rate. We learn about the status of the universe, really. But it also teaches us about the composition, the age, and the fate of the universe. Given that the universe is homogeneous and isotropic on large scales, and that it obeys general relativity, just from that, you can derive the Friedmann equation, which describes how the scale factor A, the size of the grid that you see on the left, how that will change over time. And if you can measure A, the grid size over time, you can learn about the right-hand side of the Friedmann equation, the sources, the physics that drives changes in the expansion rate. Particularly, you can learn about the energy densities of the universe, the mass, dark energy, even about the geometry. We don't directly observe A, of course, but we observe redshift, which is just inversely related. We don't directly observe time, but we can measure distances, and they're related through the speed of light. And if we look far out, we are looking far back in time, and that's how we get a lever arm on changes in the expansion history of the universe. Okay, so as many of you know, especially people who are older, it used to be enough. We thought it would be enough to just measure two numbers, just the derivative of A that would tell you the expansion rate today of the universe, the number known as the Hubble constant, which was once debated to a factor of 2 and now is debated to a much smaller factor. So I think that's some kind of progress. And the second derivative of A, once known as the deceleration parameter, because we thought again, that the universe would have been decelerating because of the gravity of the matter in the universe. But of course, that also was a surprise. Lots of surprises from the expansion history of the universe, that the universe actually is accelerating. So one of the ways we learned about these numbers and more has been by the development of really long-range standard candles, particularly in the 1990s, which seemed to be kind of a watershed time for the development and ability to make some of these measurements. So I'm going to talk about standard candles. You're probably all familiar with them, but this is the way we measure relative or even ultimately absolute distances in the nearby universe by looking at the brightness of objects whose luminosity we think we understand well. And I'm going to focus on two kinds of standard candles. I'm going to talk about type 1a supernovae. These are exploding white dwarf stars. These are stars that approach the Chandrasekhar mass limit because they live in a binary system and mass is transferred. The details of how this happens are still an area of active research. However, somehow this white dwarf reaches at or near the Chandrasekhar limit, giving us a very homogeneous explosion of a luminosity of billions of solar luminosities. So that makes them great standard candles. The other standard candle I'm going to talk about are Cepheid variables. These are pulsating stars. These are supergiant stars that live in a narrow range of temperature where there is an opacity, temperature-sensitive opacity in their envelopes that drives a pulsation. And there's a tight coupling between the period of the pulsation and the mass scale, or the luminosity scale, if you will. These are stars that are about 100,000 solar luminosities. And by measuring the period, we turn them into standard candles as well. Now, in practice, there is some additional empirical complexity. We have to characterize the small differences to standardize both the type 1a supernovae and the Cepheid variables, as well as measure the colors of these stars, because sometimes we are viewing these through intervening dust that absorbs light, but also shifts the light and allows us to account for that. Okay, so I think unless you have not been paying attention to cosmology in the last 20 years, you're aware that there really have been some changes and surprises. As of the early 2000s, it looked like the Hubble constant was around 72, and that the universe was indeed accelerating, not decelerating as once expected. And the subject of the acceleration, what is driving it, what causes it, really, I think at a fundamental level is really the big question that we have in cosmology. And there are a number of different possibilities which are often considered. That the universe is filled with a vacuum energy, what was once called the cosmological constant by Einstein. This is sort of expected in quantum theory for there to be a basic energy level of empty space, and in general relativity, a constant energy density will give rise to acceleration. And this is not a crazy idea. We even have existence proofs like the Higgs field. It could be instead that this is a dynamical dark energy. That is, that there's a field in space whose potential energy may temporarily look like a cosmological constant, but that might decay or change over time. Again, there's an existence proof for this. We think inflation occurred early in the history of the universe by a very similar mechanism. And then a third possibility is that this is a breakdown of general relativity as we approach the largest scales on which we're testing general relativity. So we don't really know for sure which of these three, or if any of these three, are right. However, number one has a great appeal in that it's very easy to calculate. It gives exact predictions if it's true. And so we call the model based on that lambda CDM, or you could call it vanilla lambda CDM, the most plain version of lambda CDM. And so the way we often proceed these days in cosmology is we do experiments where lambda CDM makes a prediction and we look for departures from that. And so what I'm going to tell you about for the rest of this talk is sort of the biggest of those tests. And the biggest, I say, just because it expands the largest range in the age of the universe. The end-to-end test of lambda CDM is to predict and measure how fast the universe is expanding. And so, as I said, we start with the vanilla form of lambda CDM, 6 free parameters, and a number of ansatz, which are tested along the way. But it's vanilla because it's filled with dark matter and ultimately dark energy, whose nature we don't really understand. And so we use phenomenology, and the simplest form of that, in the case of dark matter, we assume it is collisionless, it's perfectly stable, it doesn't change or decay. And as I said, for dark energy, we assume that it's the cosmological constant. And then we use the pre-recombination form of the cosmological model, as you see it there up on the left, to predict the physical size of fluctuations in the early plasma of the universe. For most of those, the sound horizon, we can also predict the baryon density. And then we compare that to precise measurements of the angular size of those fluctuations as seen in the cosmic microwave background, for example, from Planck. Or we could actually try to measure the deuterium abundance to get a handle on omega baryon. Either of those comparisons of the empirical to the model allows us to calibrate lambda CDM. And then once the model is calibrated, it predicts the entire expansion history of the universe with some checks along the way. But ultimately, it predicts the value of the Hubble constant today. And the best such prediction comes from Planck, 67.4 plus or minus 0.5. So this is an extremely precise prediction better than 1% by quite a bit, actually. And so a powerful test of this whole story, particularly of the dark parts of the universe, the dark sector, which today is 95% of the universe, is to go out and try to measure the Hubble constant to comparable precision. And so we started a project about 15 years ago to do that. Admittedly, when we started the SHOES project, we thought we were measuring, we were complementing the CMB to learn about the equation of state of dark energy. But now in the era of tensions and the Hubble tension, it really does look more like an end-to-end test of the cosmological model. So, but our goal has been the same throughout, which is to reach a percent level measurement of the local value of the Hubble constant, and to do this empirically, and to do this by using a distance ladder of, a distance ladder of what I would call the gold standards of the nearby universe cosmology, to use geometry to calibrate Cepheids, to calibrate type 1a supernovae. Now, we thought we could reduce systematic errors over past measurements, particularly by obtaining purely differential measurements. And I'm going to describe that later on in the talk. We also thought if we can make very strict bookkeeping, really, of statistical and systematic errors by making this a simultaneous fit, we could make a realistic comparison to the CMB. And this is not the first time, of course, that the Hubble Space Telescope has been targeted for making this kind of measurement. Generation 1 measurements were to really reach a 10% uncertainty. So this is really a generation 2 experiment. Generation 2 also in that it uses the new cameras on Hubble, Wide Field Camera 3 and ACS, which were put up in the mid-2000s. And this was not a dedicated project. This was a series of 18 individual proposals submitted to the TAC, which now, remarkable to sum this up, it's almost about 1,000 orbits. So at this point, it's quite a heavy investment of Hubble Space Telescope time. Okay, so let me just remind you what a distance ladder is. A distance ladder is really, it's very simple. It should be very empirical. And it is to start out step 1, the anchor step, where we can use geometry, and there are many ways to do this, to reach out to Cepheid variables and calibrate their luminosity. Then the intermediate step are nearby galaxies that have recently hosted type 1a supernovae, where we can return with the Hubble Space Telescope and find Cepheid variables in those galaxies. And then finally, of course, type 1a supernovae can be seen all the way to redshift 1 or 2, but we mostly just focus on the Hubble flow nearby, where their redshifts calibrate the expansion rate of the universe. So in principle, as I said, this is strictly empirical. There's no astrophysical modeling. We treat these as empirical standardized candles. There's really no general relativity or use of lambda CDM, and that's because we're essentially making the whole measurement at low redshift in the rest frame, or very close to it, effectively redshift 0.05. However, it's very important to make the measurements as differential, strictly differential and uniform as possible, particularly when we compare Cepheids between rung 1 and 2 and type 1a supernovae between rungs 2 and 3. And so a lot of the effort of this project has gone into ensuring that, and I'll give you some insight into that. Okay, let me just remind you, how do you measure geometric distances? Of course, parallax really is the gold standard for doing this. And this would be straightforward if it weren't for the fact that stars are very far away. The nearest Cepheid variables, well, not the nearest, but the most common ones are a few kiloparsecs away, which means that the parallax angle you need to resolve and measure well is a fraction of a milliarc second. And this has really only become possible to do, I would say, in the last few years with 2 techniques that I'm going to talk about now. The first of those is kind of an ad hoc technique that we developed with Wide Field Camera 3 to try to reach this level of precision for the nearby Cepheid variables. When you take an image with Hubble or any telescope, your ability to measure the changing separation between a nearby star and distant stars is limited really by how well you could centroid the star. It may be limited by other things as well, But in the case of Hubble, we can only centroid a star to about 1/100th of a pixel, which would only give you like a 1 sigma detection of parallax of a Cepheid a few kiloparsecs away. So the technique we came up with was to spatially scan the telescope during the observations to really beat down the errors in measuring the separation between stars. So as we scan the telescope, the stars go flying by. We get these really lovely looking vertical lines of charge, and we can measure the separation between any two stars over thousands of pixels. Here's a patch of one of these images. And so it's quite an interesting, quite an unusual way to use the Hubble Space Telescope, but it really does get the job done. And so then you go in and you extract those scan lines of stars, pixel by pixel. You align them in time, which is easy to do because you can see this jitter signal. The fact that the telescope bounces in the direction perpendicular to the scan means that all stars see the same jitter. And so once you time align them, that jitter aligns and then it cancels because you're only measuring the separation between stars. And so once you subtract any pair of stars, that goes away, and then you get to average over thousands of pixels. With this technique, we found we could reach 20 to 40 micro arcsecond precision. And so then we proceeded over 4 or 5 years to monitor a number of long period Milky Way Cepheid variables and measure their parallaxes. And so what you're seeing here for each of these little insets is a single Milky Way Cepheid variable a few kiloparsecs away. The back and forth motion that you see is the parallax. There's a data point here every 6 months, which is why it looks really like a zigzag. The amplitude that you see there is the parallax. The inverse of that is the distance. And with this technique, we were able to reach a 3% calibration of the Hubble constant. And we published this a few years ago. So I would call this approach 1, which is using HST to spatially scan. Now, approach 2, which is now in the last year or two, completely surpassed approach 1, is to use Gaia. Gaia, of course, is the European Space Agency mission to measure parallaxes. In some ways, similar technique to the spatial scanning in that stars move across the whole focal plane of Gaia. But unlike HST, where we have to target star by star, Gaia does this over the whole sky. And so that's much better. And in fact, it's now reached or exceeded the precision we had with the HST technique. HST is still critical to this, though, because you want to measure the parallaxes of Milky Way Cepheids with Gaia, but you still want to measure their photometry, their fluxes with HST, so that when you compare the Milky Way Cepheids to those in other galaxies, it's on the same flux or 0 point, so that 0 points cancel. And so we identified 75 Milky Way Cepheids. These are most of the known Milky Way Cepheids with long periods. Gaia has measured their parallaxes most recently in early data release 3. And with spatial scanning still, because they're very bright, we measure their fluxes. And this combination of Gaia and HST has now provided a 1% calibration of the Hubble constant, which is, I guess, maybe what I talked about last year when I gave this talk. But that is really, at this point, the best geometric calibration we have for rung 1. If you combine both those techniques plus an earlier technique that was able to reach just the nearest Cepheid variables, a handful of short period ones with the fine guidance sensor on Hubble, we have really fleshed out the period luminosity relationship in the Milky Way, particularly at long periods, which matches the periods of the only Cepheids you can really see in supernova host galaxies, which are further away. Now, if Gaia reaches its advertised precision by data release 4 or data release 5, which I think will be in the next maybe 2 years or so. This same data set, which is limited still by the Gaia parallaxes, should be good enough for a 0.4% calibration of the Hubble constant, which is hard to believe, but we really look forward to that. So best of luck to Gaia. Okay, so measuring parallaxes in the Milky Way to Cepheid variables is one of three main ways or anchors that we use to calibrate the luminosity of Cepheid variables. A second one that has also greatly improved in the last few years is to measure detached eclipsing binary systems in the Large Magellanic Cloud. Detached eclipsing binary systems are stars orbiting other stars, where you can measure the Doppler velocity to get the kinematic motion. You can measure you could time the eclipses to get the physical size of the star that you're looking at. And then you get the angular size of the star from a relation for red giants that's calibrated with interferometry, and that gives you a geometric distance. And we've also measured the Cepheids in the Large Magellanic Cloud directly with Hubble in the last 2 years. And a third, also powerful technique is to observe water masers in Keplerian motion in a nearby galaxy, NGC 4258, that has a supermassive black hole. And so those masers are orbiting the massive black hole, and 15 years of monitoring in the radio gives a very precise distance to that. And so there's been a dramatic improvement in the last 5 years in the geometric anchoring of the Cepheid distance ladder. Each of these techniques is approaching 1% with the parallaxes already there. And so that's really a great improvement. Okay, so let me move on to rung 2. You know where I'm going because there's only 3 rungs in this story. Rung 2 is the nearby galaxies that hosted type 1a supernovae, where we go back with Hubble and observe Cepheids. This is really the rate limiting step now for measuring the Hubble constant, because each supernova is good to about 6% in distance, and there's only a small number, there have been only a small number of galaxies nearby enough to do this, so you can only do as well as 6% over root n. And so the results that we presented in 2016 were based on 19 of these calibrators, and we've been working hard with Hubble over the last 5 years to expand this set. And what we're going to announce tomorrow are the results of more than doubling this sample to reach 42. This is all of the ones that are available in the last 40 years. You could see here, these last couple data points really bring us right up to 2021. And unfortunately, nature produces one of these in range of Cepheid variables only about once a year. And so that's why it's taken 40 years of collection to get 40. So you can clearly see that we're not going to double this sample again in the lifetime of Hubble. Now, here are the period luminosity relations for the first 19 of these galaxies observed with Hubble, as well as the 3 anchors now also observed with Hubble. And as I said, tomorrow we'll present another 23 hosted supernovae from these. So as I said earlier in the talk, one of the ways we've been able to really reduce systematic errors over generation 1 experiments is by making the flux measurements of Cepheids purely differential by using the same telescope to observe the Cepheids between rungs 1 and 2, and to measure Cepheids over the same range of periods and chemical abundances. And so this has been one of the ways we've improved things. The other way is by making our observations in the near infrared to reduce the impact of dust. So we observe at 1.6 microns. And so the differential extinction from dust is already very small. And then we observe the colors of the Cepheids in the optical to account for the small amount of extinction. And so you could see that this procedure works very well, particularly shown here in the Large Magellanic Cloud, where, of course, Cepheids were first discovered by Henrietta Leavitt. As you go from the optical, moving upwards here to the near infrared, and then finally the de-reddened near infrared, the precision per Cepheid goes down to about 3% in distance, which also at the same time reduces systematic errors related to any uncertainties in dust laws in other galaxies. Okay, on to rung 3. Rung 3 is the Hubble diagram of type 1a supernovae measuring the Hubble flow. And we use the data from the Pantheon sample, and just right now you may be seeing the release on the archive of the Pantheon Plus sample, which is a revision to the Pantheon sample, and the results that we present tomorrow will be based on that revision as well. But the concept is still the same. We avoid measuring very nearby, where we could be sensitive to local flows, or at high redshift, simply because the expansion rate of the universe will change, and we don't want to be sensitive to characterizing those changes, or very sensitive to it. So we use this kind of sweet spot region between about redshift 0.023 and redshift 0.15. Okay, so you combine these three steps, and this is all done as a simultaneous fit, but you can look at what the data looks like as though you were looking at one long distance ladder, rung one, where 5 different ways of measuring geometry to Cepheid variables calibrates them. The 19 past examples of Cepheids calibrating type 1a supernovae, and the supernovae in the Hubble flow. And as of last year, our best result was 73.2 plus or minus 1.3, so a 1.8% uncertainty. And this was 4.2 sigma away from this predicted value of the Hubble constant that came from Planck CMB plus lambda CDM. And so, of course, that is quite interesting, and what people often refer to as the Hubble tension. Okay, so when you look at where the Hubble tension arises from, you sort of want to take a hard look at steps in the distance ladder. And so first, looking at the anchor step, the geometric step, the individual value we get from the Hubble constant using each of these rungs separately, 72, 73, 74.2, are all consistent within the errors. There are some cross checks that we don't use formally, but are still quite interesting. They're just a little less precise. There are the spatial scan parallaxes that I talked about. There is the previous generation of parallaxes, both from the fine guidance sensor, but also from Hipparcos. And there are, Louisa Bruval did her thesis recently presenting 2 other ones, which were quite interesting, using Gaia parallaxes, but not of the Cepheid variables, but rather their companions, either binaries, which is shown here in the second to bottom row, binary companions, or cluster companions. Some Cepheids live in open clusters. Either of those provide certain advantages and certainly provide interesting independent cross checks. And these seem all quite consistent. They don't seem to provide any indication of an issue or a problem. What has really improved quite dramatically in the last year has been the release of Gaia parallaxes between DR2 and really EDR3. This is the state of, after DR2, of the Milky Way calibration. What I'm showing you here is the distance ladder in reverse. You can use parallaxes to get to the Hubble constant, of course, or you can reverse the process. You can for different values of the Hubble constant, you can predict the scale of the parallaxes. And so that's what I'm showing here is the predicted parallaxes for different values of the Hubble constant, and on the y-axis, the Gaia parallaxes. And this is for the HST sample of the first 50 Milky Way Cepheids, and it was certainly indicative of a higher value of the Hubble constant. You can see here 73 looks better than 67, but as I said, this was only good to a few percent uncertainty. Now here with DR3, which came out at the end of last year, and also more HST parallaxes, you could see things have really improved. I'll go back and forth here. If you look at the low parallax, great distance end, where the sample doesn't change very much, all the improvement you see here in the scatter is coming strictly from the improvement in the Gaia parallaxes. And that is really impressive. And I just can't wait to see Gaia DR4 when that comes along. Okay, so what we're looking at this point then is about a 0.2 of a magnitude, as seen from any of these standard candle difference in the Hubble constant. And so at the time, we looked at many systematic variants, analysis variants, where you change the way you do the analysis in ways that were maybe not terribly likely, but interesting to see if you could budge the Hubble constant. So changing, for example, the reddening law to unusual reddening laws in other galaxies, different ways of rejecting outlier Cepheids, whether you account for metallicity or not in the empirical law for Cepheid variables, the use of a single slope to characterize the period luminosity relationship or a broken slope, restricting the short period end, the long period end, expanding the sample of supernovae to more nearby using a different light curve fitter than is typically used, limiting the host galaxies of supernovae in the Hubble flow to only spiral galaxies or locally star-forming galaxies, which makes them more matched to the ones that host Cepheids nearby, or only using optical data, throwing out the near-infrared data. And these all produce only very small variations, so they don't look particularly fruitful, although we propagate the variance of these as an additional systematic error. Okay, so I am frequently asked questions about what could cause this tension. So I thought I would take a shot at anticipating some of those and provide answers. You might have other questions, and then I could try to address those. But these ones come up a lot. So could we live in a giant void that produces the 9% difference in the Hubble constant? And I have backup slides for these. No, this doesn't seem to work. Both large-scale structure theory predicts variations on the scale we're seeing of more like 0.6% in the Hubble constant. And we could look empirically for this giant void, because the supernova Hubble diagram would go well beyond this, all the way to redshift 1 or 2. And multiple papers show that these variations are very small and strongly exclude at maybe 15 sigma this void. Is the Hubble Space Telescope flux scale linear enough to actually reach this kind of precision? The answer is yes. This is what I do for my day job, is calibrate the Hubble Space Telescope, and it would be good to about 0.3% in the Hubble constant across the whole distance ladder. Do Cepheid crowding of their backgrounds compromise their accuracy? No, we now measure the amplitudes of the light curves, which would also be changed by any under or overestimate of the background, which is usually measured with artificial stars anyway. And this greatly limits the excess background that you could be seeing. Is there a difference in the supernovae themselves at the two ends of the distance ladder, the ones in Cepheid hosts and then the Hubble flow? No, in this paper by Jones, we looked at correlations of the Hubble residuals with all kinds of properties, both local and global. None of these appear to be significant, but even if you accepted any of them as they were significant, this is still only about a 0.3% change in the Hubble constant. Are the different anchors consistent? I covered this somewhat. They're consistent at the 2 sigma level, though this includes the abundance dependence, which is nicely covered in this paper by Louisa Bruval, of about 0.2 magnitudes per dex of difference in metallicity of Cepheids. Are TRGB and Cepheid distances consistent? They are, assuming you start with the same anchor and then you go to the same supernova hosts. This is nicely covered in a couple of papers recently, and this is thoroughly included now in the analysis that we will present tomorrow in the updated webinar. Can you resolve the tension just by changing the dust law in each host galaxy? I showed many examples of that in the variance, and the answer is that you cannot, but you need to take care to separate the intrinsic color of Cepheids, which is mostly set by the physics of Cepheids, from the extrinsic color, the effect of dust and how that actually changes the color. And this is nicely covered in this paper by Folan and Knox. So another question is it just our team which is seeing this from Cepheids and type 1a supernovae? And here I would say no. Over the last 20 years, I think this method has been the most widely replicated. And that's because these are, as I described, the longest range distance indicators with the most opportunities to obtain a consistent flux measurements across the distance ladder. And so here's the last 20 years of measurements of the Hubble constant with this technique, whether it's people doing this independently with different HST instruments, a different team, the Key project, with their own photometry measurements, which was done at different wavelengths as well, or people taking the shoes data, including some people from the Planck team, different supernova data, using supernovae in the near infrared instead of in the optical, but the shoes data, lots of various statistical analyses using Bayesian hierarchical modeling, all give very consistent results that don't really get us out of this. And in fact, I'll just advertise just recently, the Arakaria group took the archival data from the HST archive back at the pixel level and reproduced the photometry measurements. This was a paper by Javan Marty et al. That was published this year, and they had 1% agreement in the example that they did. And so that seems to rule out any kind of methodological issue with the photometry. Something I wanted to highlight that will come out in our paper tomorrow that I just think is really interesting. When we find Cepheid variables, we find them from their light curves, of course, but the individual light curves have very low signal to noise. So we can identify Cepheid variables, but we can't say all that much more. However, people have asked the question, are extragalactic Cepheids like the ones in the Milky Way? Are they weird in some way? And so one thing we can look at now that we have so many Cepheid variables is something that goes back 100 years to Hertzsprung. If you've heard of the Hertzsprung-Russell diagram, it's the same Hertzsprung, who noticed that there was a progression in the shapes of Cepheid light curves, characteristic shape as a function of the period of them, including some very small scale features that have been understood just in the last 20 years as a resonance between overtone oscillations and fundamental oscillations. So what you see here at the bottom is a sequence of Milky Way Cepheids. These, of course, have very high signal to noise as a function of their period, going from short periods, here's 8 days, 12, 16, 20, 28, 30, all the way up to 70 days. And you see this progression in shape, as well as this little bump that moves. This is the resonance bump that moves from the declining phase, and it moves earlier as the period grows, as you see here at following the blue arrow. Now, as I said, you cannot see this in any individual Cepheid in a distant galaxy because the signal to noise is too low. But by taking all the light curves of the extragalactic Cepheids and stacking them in period, what you see is you really reproduce the Hertzsprung progression. You see the same change in shape of the light curve. The red line there is just a spline through the data in bins, all the way down to these little bumps that you can see that are part of that resonance feature. And the envelope of the amplitude changes following the Hertzsprung progression as well. So it's really impressive that, you know, it didn't have to be this way and that we only saw them at low signal to noise, but the physics of Cepheid variables really does seem to be universal. Okay, so what is the present status then? I've described our measurements and the tension they have. A couple of years ago, there was a really fun conference at KITP where proponents of many other methods, both from the early universe and late universe, presented results, and this summary paper concluded, as I think is still the conclusion, that the tension doesn't appear to depend on the use of any one method, team, or source. You can exclude sort of any one experiment method, and you're still somewhere in this sort of 4 to 6 sigma range of tension, with early universe values in the range of 67 to 68, and the late universe kind of spanning from about 70 to 75. one way I might describe it is there's nobody who's really measuring precise values of the Hubble constant that are coming out on the other side of the early universe below, let's say, the Planck value, nor are there people from the early universe with precise measurements measuring above the local values of the Hubble constant. So that's just a kind of restatement of the tension. But the strongest tension, of course, naturally would then come from the measurements with the smallest uncertainties, which are from the Planck and Shoes teams, as I described. There have been some interesting work on the TRGB side. I'll just highlight a number of results there. A recent paper from the IFA group by Anand that has reanalyzed TRGB data shown there in the arrow. And I think there will be more of that kind of data coming in the near term. Gaia has also helped calibrate the TRGB by allowing us to measure the parallax to the nearest large globular cluster in the Milky Way, Omega Centauri, which provides a direct calibration of the tip of the red giant branch because it's the only globular cluster massive enough to have a fully intact red giant branch. And so this was work done by John Soltis, first graduate student working with me, and Stefano Casertano, who identified stars in Omega Centauri in the Gaia data, and then measured their parallaxes as a function of magnitude to determine that there was a consistent result. And that result gives a calibration of tip of the red giant branch that would give a Hubble constant of around 72. So in the same range of 70 to 75 that I've been talking about. Then there are 4 other Gaia studies that have gotten the same parallax of Omega Centauri, but a bit of a range of uncertainties. Ours is kind of in the middle there. And so I think that will be interesting to look at also as DR4 data comes out. If you're paying attention to the Hubble constant tension, you might have also noticed another slightly weaker tension, but still quite interesting to keep in mind, which is the sigma 8 tension. This is sigma 8 is a measure of how clumpy matter is on 8 megaparsec scales. It's very analogous to the Hubble constant in that you can predict from the early universe how clumpy the universe should be today, what sigma 8 ought to be, and then you can measure it locally using lensing, weak lensing, which has been done by a number of experiments, or peculiar velocities. The lensing measurements together seem to be about 3 sigma lower than the Planck value, and the peculiar velocity measurements also seem to be about, give a local value about 3 sigma lower. And so this is, as I said, something worth paying attention to. It's not quite at the level of significance of the Hubble tension, but people who want to sort of read the tea leaves and try to think of ideas of what could explain it. And thinking of ideas, I don't have any of my own, but I can report that many other people have ideas. And it's particularly tempting to think about new physics because one way these tensions set up is as an issue when you use the cosmological model to try to connect precise measurements at 2 ends of the universe. And so this is almost a cottage industry now, is to see what is possible. People have posited early dark energy, weird neutrinos, decaying dark matter. I will say most of these fall into the category of changing the pre-recombination physics of lambda CDM. And that's because this is in many ways the most successful, as pointed out in this paper by Knox and Malaya, because if you can change the pre-recombination physics of the early universe, you can cause the universe, in the successful cases, to expand faster before recombination, before we see the CMB, which shrinks the sound horizon or makes the recombination occur earlier, and that can bring the value of the Hubble constant up from the CMB value. Now, you have to do this carefully or with respect, I would say, to CMB data, because there are telltales or signatures potentially in other parts of the CMB spectrum, which in some cases are ruled out, in other cases are sort of on the edge. There was a recent paper by the ACT team claiming that in their CMB data, that they get a 3 sigma detection of some of the features of this early dark energy. And early dark energy, I'll mention, would be an episode of dark energy, scalar field dark energy, just before recombination that could cause this pre-expansion that could raise the Hubble constant to about 70 to 74. There are other indications, though, that this could be in conflict with Planck data. And so I think the jury is out, as they say, on this. However, I just saw a talk from Colin Hill, who's been leading some of this work, who promises that in the next year, the ACT data will improve quite a bit. In fact, they claim that they should get a 20 sigma detection of the early dark energy if it's there. And so this is certainly something worth paying attention to. But as I said, there's many ideas of what or how to explain these tensions. Okay, so what I think we need at this point are specific hypotheses. I often hear people sort of casually say it's new physics or it's systematics. What I think is that the data has gotten very good and really presents a formidable challenge to either of these. New physics has to be not in conflict with the present data, both the H of Z data or the CMB data. Systematics needs to also not be in conflict with the many measures, the many independent rungs, the many duplicated measurements, and I think the Copernican principle as well, to not posit that the universe is just different right over here than it is right where we are. So as I said, I think the data is just too good for making very non-specific claims. There's something going on. I don't know what it is, but we can test ideas if those ideas are provided with enough specificity. I think there's a lot of reasons for optimism in this field. There's a lot of new data coming along. People often ask me, what data do we need? And I would usually answer just the data that's coming along. LIGO will help, DESI, Roman, Rubin, Euclid. These are all experiments that will help characterize H of Z. JWST will help. Simons and S4, new CMB experiments, can look for pre-recombination new physics. There are ideas about self-interacting neutrinos, as well as early dark energy, primordial magnetic fields, things that can leave signatures in the CMB. We can keep an eye on other clues, sigma 8 that I talked about. I think that lambda CDM is still a big playground, both because most of its physics is governed by phenomenology, and also because, of course, we lack a quantum theory of gravity. So, lambda CDM is not Maxwell's equations. Perhaps there are surprises in it that could explain some of what we're seeing. I think time will tell. Finally, sort of final advertisement for the new results. Over the last 5 years with Hubble, we have more than doubled the sample of calibrators, as I talked about, to reach 42. We've also tripled the number of Cepheids observed in one of the main calibrators, NGC 4258. We'll present that tomorrow as well. We've also observed Cepheids all the way out into the Hubble flow at this point, all the way to Coma. So that's exciting. Just to show you sort of where we've been and where we're getting to. This is a plot showing the number of modern type 1a supernovae that have been calibrated with Cepheid variables with Hubble over time. And so when we got started with this, there were only just a few. The results we reported in 2011 were here, this blue line. The results in 2016, this blue line. That's the last major update we have done for the calibrators. And so what we'll present tomorrow will be up to this blue line. And as I said, that brings us pretty much up to date with all that nature has given us in the last 40 years. And so it's hard to see how we're going to double the sample again in the future. The errors we've realized over the last 15 years in this quest to measure the Hubble constant, the value has not changed very much, but the uncertainty has come down by attacking these different sources of uncertainty. And what we hope to reach soon would be 1.3%. And then with improved Gaia parallaxes, that 1% target is just about in range. As I said, there are new experiments coming online that will certainly weigh in on this. I look forward to that as well. So I think this is a developing story. Okay, so I'll wrap up here. Final thoughts. The discrepancy has been in the range of 4 to 6 sigma. It really depends on what combination of probes you use. So that makes it, I think, quite interesting. Here's a recent review by Eleanor Di Valentino showing many of those. As I said, a simple way to summarize that is just simply there's really aren't any precise late universe measurements coming in lower than the early universe side. And I would say the same is true in the other direction. It appears to be robust. I think it would require a number of catastrophic failures to avoid it. So I think it's very interesting, unless you have a very, very strong Bayesian prior on vanilla lambda CDM, or you're willing to throw out a lot of data. I think it's, as I said, worth paying attention to. But as I said, at this point, we really need ideas, explanations, whether they be ideas about new physics, errors in measurements or whatever that are specific, because we can test them because the data has gotten very good. So I will end there, and thank you.
Thanks so much, Adam, for this great, outstanding lecture, and so clear, stimulating at the center of cosmology today. And we open then, as usual here, the session for discussions, comments, reactions, questions. So please, participants, hand up the hands, and then I have one first question here. There is one. So Philip Helbig, please summarize your point to address your question to Adam.
Yes, just a quick question. You mentioned that there's no shortage of explanations for this tension, but presumably many of them are ad hoc, despite how the authors might try to justify them, ex post facto, so to speak. Are you aware of any explanation for the tension which was suggested before it was seen in the data? A prediction of the tension?
Right. Well, that's a very good question. And I don't think I've ever heard that question before. Even though I tried to anticipate so many questions, I don't really think anybody anticipated it. I think we thought, perhaps we were still reeling from lambda CDM, in the early 2000s. We just thought, okay, that's, probably, these will match or connect. On the other hand, this is the nature of cosmology, as we say, let's start out with the simplest model. So, in the case of lambda CDM, it's natural to assume things will be vanilla, dark matter, and dark energy. So I would say, no, there were really no predictions of it. When you say about the ideas being ad hoc, I will say some of the specific mechanisms are kind of ad hoc, but I will say the general idea that there's additional complexity in the pre-recombination version of lambda CDM, I think that's generic to many of the ideas. And I think that's quite interesting. I don't consider that very ad hoc. I think what we're realizing now is is something that needs to be tested. It needs to be tested both with better CMB observations, as well as by these comparisons between, the predictions and the what we see in the present universe. And so I think what we're going to learn in the next few years is the pre-recombination universe as vanilla as, our first order guess was.
Interesting times.
Thank you. Thank you. Other questions, points, reactions? So the lecture was very clear, and if Adam, you could add something. I mean, the floor is yours. I have one comment, but I prefer leave before participants, and you, if you would like, to add some more thought or to share with us some of your points.
Sure. I don't think I have anything else to add except to say, look for whether, I gave an address for I'll return to my first slide. If you want to go to, oh, there it is. Yeah, this I missed the last bullet here. We'll provide an update tomorrow at noon. So that would be 6 o'clock European time. And if you follow that, if you click that link or grab that link, or if you don't, I could put it in the chat or email it to you if you ask me. Then you'll get another update there, and those papers will be out at the end of the week. And I think that's all I had to share.
Yes, we have the link. We have the link to register, and then Daniel Skolnik send the information connection. And,
Okay. I just put the link. I just put the link in the chat. So,
yes, yes, please. I prefer. I mean, you could, of course. I will see in an. I will go. I will go in some sense. Said I will connect to a webinar.
Okay.
I have already received all that, and it's at noon in the time of yours.
Yes. And
So,
again, I apologize for not having the results in time for this talk. It was just many months ago when
but I mean,
this time.
it's,
But
welcome.
Sure, but we're doing a webinar because I guess that's what you do in the era of COVID. In the old days, this just would have been a conference or something. But anyway,
Of course,
that's the way it goes.
and it's useful that the collaboration organize the webinar and put. And do you think it will be surprises? I mean, real surprises?
Well, nobody likes to be told ahead of time where it's not a surprise, So I just you'll just have to see. keep your expectations low and you won't be disappointed.
Of course.
Yeah. This is yeah.
And I just want also to add a quick point. I mean, last year, and you mentioned, I comment that one of the, at least for my understanding, a better explanation or more direct said to this mismatch or tension or natural explanation is the fact that the vacuum energy or so-called cosmological constant will be varying, and a little bit it will be in the pre-recombination, as you said.
Right.
Perhaps not in the pre-recombination, as you said
before. Right. Yeah, so I can address that. So you might say, oh, why don't you just say it's not a cosmological constant, that it's a dynamical dark energy,
yes.
And so the universe is expanding faster. And those explanations have been disfavored more by the data than anything else. That we have baryon acoustic oscillation data and high redshift supernova data that spans the range between redshift 2 and 0 that show an expansion history that looks a lot like lambda CDM. It looks a lot like W equals -1. Now, there's still wiggle room there, but I would say, that looks less attractive.
Yes, but what I am saying is after all, we know that inflation, the cosmological constant is not a constant, it's a slowly, it's a quasi de Sitter, it's a quasi cosmological constant. Right. And it appears, I have a paper just published in Physical Review D this 6 December from the previous, Planckian or trans-Planckian physics to the late dark energy, and it appears that the cosmological constant is not a constant, but said a vacuum energy rate, as it's the Hubble rate. Even, of course, in the late is as you said, but in the most early, it appears that after all is the vacuum, and the vacuum in physics even if one of the phases in one of the phases is more dominant, is less dominant. But the vacuum in physics is always there. And that is what appears to me that the vacuum and the vacuum density and it could be a very slowly, but not just a constant
Sure.
even. And
Right.
that is an ingredient in some sense, which is not ad hoc. I mean, it appears, and it could be incorporated to better, I don't know
Right.
if for H0, but to better all
Right.
the data.
Right. Well, there may be more surprises. As I said, I would look towards some of the new CMB experiments, the Simons Observatory, S4, things like that, as providing any, additional insights there. And with that, I think I'll sign off. And thank you very much for hosting me.
Yes. And so I want to proceed to a toast. I have my own champagne here.
Okay. Very good.
As always in the school to wish you the best and best wishes.
Thank you.
And best wishes for tomorrow and for the year. And as always, with one of the symbols of this school, the true French champagne, to wish you a second Nobel Prize, because we always.
Thank you. I wish it for everybody to be healthy, and that we can all see each other in person sometime soon.
And as far as it will be possible, we have prepared the Eiffel Tower too, as you have seen in the posters.
Yes.
To accompany H0 and the H0 award. So, Adam, keep safe.
All right, you too. Everybody be well, and thank you again.
I see you tomorrow.
All right,
bye, and thank you very much, all participants.
All right, bye.
Bye, Adam. Bye.